All right. So the homework assignment. Well, first we need to go do some I/O stuff, right? So I think down here.
We need to put the 1 in memory address
Yep.
and 8192.
Yep. So what we're gonna do is we're gonna create a label. So for doing input, in fact, we can actually steal this, I think, from Zybooks. We roughly have. Just grab the I/O code. I/O is in part 1 or part 2?
Part 2.
Let's see. No, I/O is in part 1.
Oh, okay. And I have like the 7 too, the chapter 7, I believe. I had to go to chapter 7 too. Chapter 7?
Yeah. So here's our get input, right? So get input, we load something into an 8190. Well, we load memory address 8192 into a register. So we add into T1 0 8192s, or I'll just steal this line and we'll doctor it a little bit. So we're going to do that first because we're doing some I/O stuff. All right, so we're going to do that, and ours is just T1, no commas, right?
No.
That's Karan's job. All right, so let me actually just get rid of this other stuff. All right, so we'll put 8192 into T1. Then we have this what we're loading a 0 at memory location. Well, we're loading an 8192 into T3. So we have to write this in our language version. So we're calling this get in like that. So we have a label. And then we're LW T3. And we don't have this offset thing. So ours just looks like T1 like that, right? So this will load into T3 whatever's in memory address 8192. In actuality, didn't we write ours that we could take a direct memory address? I think I could actually just say 8192 here and have it still work. I think we wrote it that way, but we'll keep it like this for now. All right, so we have a label called get input. So we're just going to keep re-leveraging T1. So T1's just always going to hold this 8192 address. All right, then we're going to check T3 to see if it's equal to a 0. Yay. All right, so if T3 is equal to a 0, then what are we going to do? We are going to set T2 equal to 8196. So that's our kicker thing, right? That's for actually doing the keyboard input. So we'll add T2 0 8196. I'll probably end up reorganizing this stuff a little bit. Then we'll load from 8196 into T4. All right. And when we do that, what that's going to do is that should trigger input for us, right? So let's go ahead and let's see. So this is, we'll have an 8192. We load into T3 8192. If that's currently a 0, that means we read some stuff in. Is that how we implemented our input? We can go all the way up here because I think we trigger it on 8192, don't we? Yeah, here. So when we do an SW, if 8192, if our memory location is 8192, then what do? We also then get a register value, whatever the register name was, and we check to see if it's equal to 1. So if there is, and what register should that be? So we are having 8192, and we need to load in a 1. That's when we ultimately will set 8196 to our read. So here's our 8192. We're setting the, so we will branch to done if it's equal to 0. If it's not equal to 0, that means it was a 1. So
I ended up taking that loop out.
well, this isn't a loop. I just want to do our the simplest version of our I/O, so we can do it this way because we wrote ours to allow us to do direct memory. So I can do this. Is that on the store? We're just going to do this. We'll add I, T0, 0, 1. So T1 currently holds a 1. Then we will SW, and if we look at how we wrote this, which is equivalent to how MIPS works, we wrote ours, let's see, where's our 8192 thing here? That's higher up. Where did I put? Oh, there it is. There it is. So when I store something, if I'm storing a register location into a memory location, if that register value is a 1, then it's going to trigger I/O. All right, so back here in my code down here in the bottom, I'm going to store a 1 right here. Then I'm going to do an SW T1 8192 because we support that. Ours supports a direct memory location. Then I'm going to do LW, we'll call it T2, 8196, which is where the input should be. And then well, that'll read it into T2. Oh, we'll be able to see it because we do a dump, right? Okay, so I store 1 in T1. I store that number 1 into 8192, which will trigger I/O. Then I'll load it from T2. I'll load into T2 from whatever's in 8196, which is where my read read in. So if I hit run on this, it's going to pop up. It's waiting for me to give I/O. I'll give it a 5. It should put a 5 into well, it'll put a 5 into 8196, which should, then we're loading it into T2. Okay, so that's done. So 8196, there's our 5, this guy right here. And then it's also in T2 up here. Here's our T2, and there's our 5. All right, so this reads something into T2. right? So this reads a number. Okay, so this will read in one number into T2. I'm just going to do this real quick.
I also feel lazy to create a subroutine, so just copy the code and putting this here.
All right, so this will read in one number, put it in T2. This will read in another number, put it in T3. We can test that to make sure both of them were read in by doing a add T4, T2, T3. So that should add our two numbers together, storing the result inside of T4. So if I put in a 5 and a 4, I should have a 9 inside of T4. 5, 4. Where's my T4? I can't scroll very well. T4 is a 9. All right. So we read in two values. So up to this point, we have two values read in, one in T2 and one in T3. All right. So now the homework assignment says to do what? It says we got to decide which of those numbers is smaller. All right. So we're gonna how do we decide if one number is smaller than another number? We have to use that less than trigger thing. What's that called? STL? SLT? STL?
Yeah, I think it
SLT. All right, so we're going to say SLT and what gets set? So what?
Register and for true or false, then.
Well, here. So we're going to say, we'll say SLT, and SLT takes what? Does it take a destination register, or does it always set?
It's a destination, like a true or false.
Okay, so I'm going to set T4 equal to SLT of T2. So T4 will be set to a 1 if T2 is smaller than T3. Correct? Okay. So now I can check T4. So I'll say, yeah, branch of equals T4, and can we say 1? Does branch of equals?
You can compare with 0.
Yeah, that's true. 0 register. So if T4 is equal to 0, that means that actually T3 was, I need to give it a place to branch to, but that means that actually T3 was the smaller value, right? So let's do, we'll call this guy T3 smaller. That's the name of my, the branch location is T3 smaller. All right.
What is that one doing? That line?
This checks to see if T4, which is the result of our SLT, T4 will hold a 1 if T2 is smaller than T3. It'll hold a 0 otherwise. So if T4 is equal to 0, that means that T3 was the smaller of the two values. Make sense? So if T4 is a 0, T3 was smaller. Otherwise, T2 was smaller. So again, just to keep this, how many registers did I give myself up through
I
what?
think you have a.
How many can I keep reusing? Because we're just going to hack this. We have through T6.
Got a lot.
That's okay. We don't need IO anymore. So we can burn those. We're done with those guys. All right. So we'll go ahead and we'll set T1 to our smaller number. So we're here. T1 will be, and then we'll do T2.
Or you can use be not equal.
No, we'll use labels. Labels won't be a problem. So I'll use T1 and T5. T1 will always be our smaller number, and then T5 will be the other guy. All right, so if I'm here, that means that T2 was smaller. So I will add into T1 the result of, this would be T2 and 0. So that will store into T1 the value of T2. T2 plus 0 will be T2. All right, so T1 will be equal to that. And then I will set T2 equal to T3.
Three.
Are you trying to switch them?
Well, I'm just putting T1 and T2. T1 will be my smaller value. T2 will be my bigger value when these guys are done. So we'll say add T2, and we're going to put in T3 and 0. Okay, that's what we do if T2 is smaller. Okay, so now I'm going to just do a jump to our loop, something like that. And I'll put a placeholder in here for our loop. Otherwise, we're going to have a T3 smaller, and we're going to steal these two lines. I think we wrote this to work like this. And we're going to put a T3 into T1. And we'll put a T2. Actually, we don't even need to change anything. It's already in the right place. All right. And then we'll just naturally bang into loop here. So what do? We check to see if T3 is smaller. If it is, what do? We go to T3 smaller. We set T1 equal to the smaller value, which is T3, and we leave T2 alone because T2 is the bigger value. And then we naturally hit the loop label. Otherwise, if T3 was not smaller, I'll set T1, we just continue on. I'll set T1 equal to T2. Then I set T2 equal to T3. So, and then we will jump to our loop. So any way you cut it, when we get to loop, T1 holds our small value, T2 holds our larger value. Make sense? All right, so far so good? Then, what are we supposed to do next? Display all the numbers between the smaller number and the larger number to the screen. Okay, so how do I display? Wasn't that the 8200 something or other? Don't I store SW82? Is it 8200? Yeah.
Yeah, you do that.
Store, yeah.
You can search for 8200.
Yeah, but this is more fun-ish. Maybe not. Next. There we go. All right, so in set DM value, so that's going to come from SW. So if I do a SW and I pass it a mem address of 8200, then it will display the new value. So whatever I put in 8200, it spits out. That's how it looks like it works to me, right?
Yeah.
Okay. So let's just have it print one thing for right now. Let's just have it print, actually we'll display two things. Let's display the smaller and then the larger number just to prove that our logic up to this point is fine. So we'll do SWT1 8200. So that should give us the smaller of my two numbers. And then we'll do S1 or SWT1 8200. That should give us, I'm sorry, T2. That should give me my larger of my two values. So let's just make sure our values are right. So I'll do a 3 and a 9, but we'll test it two different times. So I'll do a 3, I'll do a 9. So this should print out 3 then 9.
It should be up.
Oh, yeah, there we go. 3 and 9 is my output. We'll run it again. I'll do 9 and 3 just to make sure our logic works for them being opposite. 9, 3. And we should get 3 and 9 as our output, and we did. All right, so far so good. All right, so we're reading in two numbers. We're making sure we get the numbers loaded in. T1 has the smaller of the two, T2 has the larger of the two. Everybody's happy? All right, so now our goal is to do a bunch of displays of all the numbers between there, right? Okay. So what we want to do is we can decide if we don't care about the value of T1 when all is said and done, we can just keep we can just keep adding up T1 and printing the value. So the first thing we would do is we would SW T1 8200. That'll print out the current value of T1. Then we will say add I T1 1. So that'll make T1 1 greater than it used to be. T1 plus plus. Right? Then we want to
Usually add the T1, T1, 1. Usually
because it takes 3 parameters.
yeah.
So it's that. So store into T1 the current value of T1 plus 1 for add immediate. Okay. So that'll increment T1 by 1. Then we want to either branch back up to our loop or finish. So I'm going to give ourselves a little label down here at the end. So we're going to say, let's see, we can,
Equal to
well, we can do this a couple different times. There's a couple different ways. If we don't care if it's equal to our last value, because what will happen here is we'll do T1, then plus 1, plus 1, plus 1. Eventually, we're going to get to T2. If we want to print out T2 as well, then we need to make sure we go up to and including that guy. So what we can do is we can say we want to branch back to loop if T1 is less than or equal to T2.
Your question is what you asked us is to put the number in between.
In between, yeah.
I did that
didn't
not
mention
inclusive.
the-
Yeah.
Okay, well, which fine. That makes it easier. But we can. I mean, that's a question. Oh yeah, yeah. Because what I'm having to do here is if we want to go all the way up to that number, we're going to have to do a less than test. Because until it's not less than it, we'll do one more print and then finish. But if you did between, so did you not even do T1? If it was 3 to 7, you did 4, 5, 6?
I added 1 and then I
Okay. Is that what everybody else
actually
did?
no. I did it way different.
Just tell me what you want the output to be. You want the output to be,
Not
if it's
inclusive.
3 and 9, do you want it to be 4 to 8?
Yeah.
Look at it
Yes.
inclusive and
I understood it was
I didn't
the
do
betweens, like 4 to 8.
Okay. Fine. Then we'll do this.
I understood that what he wanted to do was like in between. So
Okay.
4 to 8.
So not inclusive.
Well, good. That makes it easier. I asked you an easier question. So I'll add 1 to it. Then I'll print it. And actually what we would do here is, oh, that's fine. We'll just leave it at that. So this does assume that they are not the same number. We'd have to do some, but we'd have to do some other testing to see if you entered in 2 numbers that were between 5 and 5.
Yeah.
Your output would then be nothing.
Yeah.
I wasn't necessarily expecting you to test that, so we could just assume one is smaller than the other one for the sake of this
It's
whatever.
not that hard. I added it up above right before you start looping.
You added what right above?
I added the first thing I did before I set on less than was branches equal the 2 registers.
Oh, you just jumped past if they're the same. Yeah. So you could actually do that as the first thing inside of loop if you want. In fact, you could do the count that way. You can say BEQ T1 T2. If they're equal to each other, we can branch to done. Right there is the first line of the loop. Otherwise, what are we going to do? We're going to, at that point, we know, it still doesn't get us we're going to add 1 before that. So when I get down to loop here, T1 is smaller. I'm going to say add I, T1, T2, 1. So I'll add 1 to the smaller number initially. So it's already 1 bigger. Similarly, when if T, so this one I'll do the same thing. I'll do an add I, T1, T3, 1. So anyway you cut it here, T1 is the first value that is in between our range. Then we'll loop. If the two values are equal to each other right now, we're done. Otherwise, we will display. Then we will add I, T1, T1, 1. And then we will jump to loop. So once they're equal to each other, we branch to done. Otherwise, display the current value, add 1 to it, jump back to loop, check to see if they're equal to each other, display the value, add 1 to it, jump back to loop, yada, yada, yada. So if we do a 3 and a 9, we should get 4 through 8. 4 through 8.
Where is it?
I did completely different. I like created the counters and everything like we usually do.
It's okay. I mean, that's kind of the whole purpose of the next chapter. Chapter 4 talks about inefficient assembly code versus efficient assembly code, right? So, I mean, what we did here was a fairly hard-coded way. We could have been, I was okay with my use of registers. I did reuse T1 and T2, but, you know, we should have probably had a label to jump to for doing the I/O. Could have done a couple of things like that to make it cleaner. But bottom line is that the job of a compiler is to take high-level code, because writing a loop that loops through all the numbers between 3 and 9, for instance, read in 2 pieces of information, then write something that goes through all the numbers between 3 and 9, and then exiting the program. If we wrote that in Java, let's say, and then we compiled it, ultimately it's going to turn into something that looks like this for those instructions. And all we care about, let's call it 99% of the time, is that it's an accurate representation of it. Most of the time, we don't care how fast it is. Because most of the time, our computers are so fast it doesn't matter. We're doing billions of instructions per second, so whether you did it in 22 lines or 55 lines, it doesn't matter. But every now and then, there might be something where it would be too slow for the type of problem you're solving. All right. So, can we just, everybody understood what I did here? Can we just call this good? I can put this up on my prog up on Slack.
How many credits you are giving to yourself?
Oh, for that?
Yeah.
Oh, I guess 100. It works. I mean, if I was doing the assignment, I probably would have done it like that, just because it doesn't take very long. It's not like a super complicated assignment.
It's because you asked us how you evaluate the assignment you are doing.
Well, think back to maybe the first class you ever had with me. I would rather have inefficient correct code than efficient incorrect code. Always solve problems in the way they make sense to you first. Every now and then you might have to go and do something funky because the type of problem you're solving is one of these weird time complexity problems or something like that, where the obvious solution wasn't necessarily the solution that that was obvious. Yeah, that was let's see what I want to do here. Wasn't necessarily a good solution or an acceptable solution. Okay. So, questions on that one? So most of you use the Books emulator?
I didn't use that.
What fun is that? We spent. What'd you test it on?
The book simulator wasn't working for me and I couldn't figure out
She had this really weird thing that
the book wouldn't let her put an input in, and so it just kept looping.
I
Yeah.
was stuck in my first like infinite loop, and I couldn't get it out because it wasn't making an input, so I just looped it through on paper.
But you didn't want to use our
I
interpreter?
couldn't figure that out.
It seems like we spend days writing an implementation of a MIPS processor, and you use it. She's going to use this junky one that comes pre-built into Zybooks. I mean, we saw the thing doesn't even work.
It was really good. Well, maybe it would be the same thing for using our own, but it was really nice because you can step through it.
Yeah.
And
And,
like
like,
the
do a lot of-
visualization, you could see
Yeah,
it,
it was really
everything.
nice.
Mm-hmm.
So ours was better, is what you're saying.
Yep, that's it.
Between now and 10 o'clock, yes.
That's a good answer.
So I have a question.
Yup.
Because I'm using the Zybooks, and you don't really need to, because when you're writing for the scheme, we need to set to 1 whenever we enter input. But the
No.
Zybook says that, yeah, like to just.
Oh, you need to
Yeah.
put in 8192 a 1.
Yes.
Yep.
Correct. But the Zybook, we don't need it all. Whatever is on the screen controller, it automatically puts the 1 there without writing any code.
Yeah, so it cheats.
So it takes the 8196 takes the value and already set. Then I was a little confused because the scheme does a little different. So I went to the chapter 7.
No, our scheme does it correctly.
Okay.
That's what it does.
So the scheme says that a keyboard controller puts a press the key into a register having a location 8196 and sets 8192 with 1. So what is the, I don't know.
Well, it's a both and. So you're saying the keyboard controller, right?
Yes.
So you have a keyboard hooked up to a computer, and you go and you press the number 5 on it.
Okay.
What happens when you press a 5? What happens when you press a 5 is you put a 1 into 8192, then it captures that 5 and puts it into 8196. That's what that 5 button does. Whenever you press any key on a keyboard, it's triggering that logic.
Okay.
Load into 8192 a 1. Prepare for input from the keyboard. And what does that mean is get 8196 ready because we're about to throw something in there. And that's then when the 5 would fire in there.
So I was understanding after spending hours trying to understand, I understood that part. But then I got to the chapter 7 and it says that first the 8196 takes the number, then it sets 8192 to 1. So
That doesn't make sense. Because the way CPUs work is you need to effectively notify them that I want you to read in a value. So the putting a 1 into 8192 is the act of notifying the CPU to read from the keyboard. So that's what triggers it to go into read mode. That's what has us have it pop up with the read instruction. So, I mean, that's how CPUs work. They have to be triggered to prepare for I/O. I think didn't we write it last time? I kind of wrote a program that if you print a bunch of stuff out, it goes really, really slow.
Yeah.
Yeah, because
You have that.
doing anything I/O related to a CPU is constantly interrupting the CPU because the CPU is not in control. CPUs can sit there and crunch numbers all day long, but the second you say, "Hey, CPU," you toss them 1 into 8192, the CPU goes, "Oh, okay, I got you. Go ahead and do your thing. Let me know when you're ready." When are we ready? As soon as something hits 8196. Now the CPU takes back over. That make sense?
yeah, that makes sense. I don't know what the book was.
Okay. So there's our working assembly code on our awesome implementation of the MIPS processor that is better than the crappy broken book one.
You should suggest a book to replace their.
I'm going to. It's in my to-do list. because we don't have that much to do on the simulator on Scheme. I'm gonna do that. I'm gonna send it to Zybooks and say just replace your stupid one with the Scheme one.
Yeah.
And then you can put the two classes together.
Didn't you ever wake up one morning and say, you know what? I wish there was a MIPS processor written in Scheme.
Oh yeah. That's my dream.
Every morning.
Every morning, you think that? Man, it's so good. You know what else?
For computer science brain, you're just like always thinking.
You know what else I wish? I wish that we could sit in class sometime and make our own compiler that compiles from, let's do it in Java. Are we, most of us, familiar with Java at some level?
Yeah, let's do Java. We love Java.
We love Java.
Java copy, Java code.
Well, it's going to be awesome because what we're gonna do is we're gonna write in Java a compiler which takes C code as input and outputs MIPS code. Yeah, it's gonna be awesome.
I saw that you are going to write it in Scheme.
What
So
fun
we're
is
done-
that?
We're done with Scheme now?
Well, for this class,
Are you serious? It's over?
not if just for now. I don't even know what the next chapter is. We'll come back if it makes sense.
Well, I'm rusty. Okay.
But it wouldn't make sense to write a compiler in Scheme.
Well, you said it.
No.
That was an assembler. Oh my god.
Let me bring up your stupid slide.
This is why it's not.
There's your stupid slide. We did this in Scheme.
It's awful. There's a picture in the book about that.
Now we're doing this. So why'd you need a slide?
Because when I go back and I study for the exams, it's gonna be this first before I look back at the book.
Well, right, but I just wrote the stupid slide not that long ago, and you got it wrong again. Well, didn't we already write that? No!
But you're like combining 3 different languages, so it's all getting mushed.
It's all the same crap. What do you mean combining 3 different
No,
languages?
You're saying we're writing Java.
Well, let me draw you a picture.
A stupid slide is not allowed. We need a second stupid slide.
Hey, let's put another stupid slide on here. So, okay, so we are writing a Java program.
Yeah, I got that.
Okay. Now, this Java program is going to function as a compiler. All right, so that's what the Java program is going to do. He is going to take a C code as input, and then MIPS assembly will be the output.
So no more Scheme.
Then
Then
we have a Scheme program. And this is our assembler. Blur. There. And this guy takes MIPS assembly, which, yeah, that's what this guy outputs. And then we can pass it into our Scheme program, and he will output, well, he will effectively run the program. Oh, underscores.
So why are we writing the compiler in Java if it's going to be reading in C?
You could write it in any language you want. Pick your language.
Human language
Java.
We're just writing it in a high-level language because typically, I mean, realistically, in real life, compilers would probably be written in, well, it's actually an interesting question. Maybe in C, but not necessarily. It wouldn't be written in Java in a virtual machine, but it could be. There isn't a great reason for that. But the first compiler had to be written in assembly.
Yeah.
You had to write the initial compiler in native syntax, native code for the CPU.
The first is specific. But because C, the compiler of C is very like matured, so it is
Yeah.
well done.
But we'll do it in Java to be friendly. Because the focus here is if I have C syntax, which looks like Java syntax, and probably the stuff we're going to tackle here would work in Java. I don't think we're, solving all the world's problems in our compiler here. I think we're doing something relatively simple. And now that we're short on time, we'll probably get most of a full working compiler done, but not all of it. So I only have 2 hours now. No breaks. All right, so, but this is effectively what we're building here. Somebody comes along and writes something in a high-level language, runs it through a compiler. We're going to write a little simple compiler thing in Java. It will output assembly language for some CPU. The architecture we're going to output for is the MIPS assembly. We can then, theoretically, we should be able to take the output of this program, of our compiler, feed it into our scheme implementation of our CPU, and have it run and actually execute. So we should be able to sit there and have a C program and compile it out at the command line and see it run. And then we should be able to run that same C program syntax through our compiler, giving us MIPS assembly, and then have that run in our CPU that we built in software and have it give us the identical output. That's how it works. Does that make sense?
Yep.
All right, so let's look. Did we read this chapter already? Yeah. Was it hard?
I thought 4 was difficult. It took me, I think of all the chapters I've read so far, 4 took the longest.
All right, let's start with something easy. Assignments. I think it's easy. I haven't looked at it. But I looked at this. All right. So they're saying if our C code, ninja, if our C code looked like this, and they're actually going back to traditional C, although we can make ours better than that. Fine, whatever. We'll do old school C. So old school C says you have to define the variable first, then you can use the variable. Where most of us, if we're writing Java code, we would say int x equals 7. Right? We'd write it all at once. Not the end of the world. There's not a great reason why we couldn't write our interpreter that way, but let's just say, what are the cool kids they say? Whatevs? Is that a thing?
That is a thing.
That's a thing.
At least it used to be.
But is it still a thing?
I'm not up with the cool hip like those.
I don't think it's as popular anymore.
Between now and 10 p.m. it is. Right.
Maybe middle schoolers.
Yeah, I don't even think my sister says that. And she's
Like
in
still?
high school.
See, so I get along with middle schoolers. That'd be dangerous. I shouldn't let me hanging around playgrounds. Guys over there with the van. They have like major police like in elementary schools and stuff now. This is a crazy world we live in. It's junk. Okay. So old school C made you define the variable first, then use it. You've actually probably seen this before when I've written, if you've been in one of my classes, I wrote an old C program. When I have a for loop, I don't say for int I equals 0, I is less than something. I say int I, and then I say for I equals 0. I don't define it inside of it. It's most modern C compilers would compile the more recent way of doing it, but technically an old-fashioned single-pass C compiler might not. They're keeping things relatively simple, so we'll just model that.
But does that mean actually the int I is out of the scope?
It is, yeah.
So
It wouldn't be part of the local for loop scope in old C.
So it means, yeah, that's what I mean. The old C, the scope concept is not really the same as we have.
We lose the ability to have a scope that lives and dies with a for loop. We lose that.
Yeah.
Okay. So one of the things we have to, I assume The book talked about like managing registers and things like that. All right. So let's just talk about variables. So we kind of go back to this idea of, how do human beings solve problems? Well, one of the things we need to be able to do is we need to be able to store stuff, right? So that's our memory, that's our variable stuff. Now, inside of our computer, are we due for a break yet? Are we? Everybody's get up to pee. Do we need to break? Should we take a break? All right, we take 5 minutes. 5-minute break, because I'm about to jump into something that's going to take forever.